In Lecture 8, we're going to look at reactions of aromatic compounds. The primary type of reaction in this chapter is electrophilic aromatic substitution, and kind of along with that comes nucleophilic aromatic substitution. We're also going to look at something called a pericyclic reaction, which is known as a Diels-Alder reaction. The Diels-Alder reaction is in the Wade textbook's chapter on conjugated systems and aromaticity, not in the electrophilic aromatic substitution chapter, but they are related because they both involve reactions of aromatic compounds. So let's start briefly with the Diels-Alder reaction. This is again called a pericyclic reaction because it can be used to make a ring. German chemists Otto Diels and Kurt Alder discovered that alkenes and alkynes that have electron deficient groups will add to conjugated dienes in such a way as to form six-membered rings. This is the general form of the Diels-Alder reaction. What we have is a diene, a conjugated diene. Remember, conjugation is alternating single and double bonds. So double, single, double. That's our conjugated diene reacting with an alkene or an alkyne that has an electron deficient group. This is an electron deficient group. It is withdrawing electron density from this pi bond. And these two molecules will react only in the presence of heat. No other chemicals are required. And you'll get a six-membered ring. And in this case, it would contain a double bond. You can see the mechanism arrows here. Basically, the diene acts as the nucleophile and donates its electrons to the electrophile, the dienophile we call it, with the withdrawing group. So these electrons basically attack the dienophile. Then the dienophile uses its electrons to feed back into the diene, and we move one pi bond around. That gives us one bond here, one bond there, and we move the pi bond into this position. That gets us our six-membered ring. Here they've colored the atoms that were involved in each piece. We've got the blue atoms from the diene, 1, 2, 3, 4, and we've got the two atoms from the dienophile in green, 1, 2. The Diels-Alder reaction is more generally called a 4+2 cycloaddition. You can see that we're adding a piece of 4 carbons and a piece of 2 carbons, and they are adding in such a way as to form a ring. So it's a 4+2 cycloaddition. The mechanism is one step. It's a concerted mechanism. That's important because it also explains the stereochemistry that I'm going to show you in a few slides. So like we've said, the diene acts as the nucleophile, the dienophile acts as the electrophile with some withdrawing group. So the nucleophile adds to the electrophile will donate back in. That gets us our two connecting bonds, and we move one of our pi bonds from the diene around into the middle, and there's our ring. That can occur with an alkene as a dienophile or as an alkyne as a dienophile. In either case, we generally need some withdrawing group. Now you'll notice that because the dienophile with an alkyne has 2 pi bonds, after we use one of them to make a bond to our diene, we'll still have 1 double bond left over. So depending on whether we start with an alkene or an alkyne, will determine whether we have 1 or 2 double bonds in our ring. Now, what's cool about the Diels-Alder reaction is that it can give us access to complex structures from relatively simple components. We can make complicated ring structures, a 6-membered ring with, in this case, it's 3 substituents, 2 methyl groups, and the cyano group, or we can make bridged bicyclics by starting with 1 ring and adding the dienophile to that. We can make bicyclics that are fused rather than bridged, again by starting with a ring as the dienophile and using a linear structure as the diene. Again, these can have different substituents on it. Here we've got methyls. Here we've got esters as our withdrawing groups. Here we've got an ether on our diene, and this kind of diester, this is a acid anhydride as our dienophile. We get complicated structures from relatively simple molecules. There are a few stereochemical requirements and outcomes for the Diels-Alder reaction. The first is that the diene, which again acts as our nucleophile, must be able to achieve an S-cis conformation. Now, what do I mean by S-cis? Well, we know what cis means as far as a double bond goes, but when we're talking about S-cis, the S stands for sigma. So here's our diene, and you'll notice that the conformation of our diene is cis around that single bond. You see the cis geometry of this molecule, but it's only cis around a single bond. Now, of course, rotation is always possible around a single bond, which means that there will always be some equilibrium between the S-cis conformation, or you rotate around that single bond, we get to an S-trans conformation. Generally speaking, the S-trans will be more stable because in the S-cis conformation, as they show you here, these two H's will start to collide with one another. So the S-cis is less favorable, but in the Diels-Alder reaction, our diene must be able to access that. Now, what do we mean by access? Well, it has to have a relatively equal equilibrium between the two of these. For example, look at this ring structure. Here's a diene. It's a conjugated diene, but because of the ring structure, the diene, double bond, single bond, double bond, is locked in that S-trans conformation. We can't rotate around that sigma bond and get us back into the S-cis because it's locked in that ring. So this is not a suitable diene for our Diels-Alder reaction. On the other hand, in the cyclopentadiene ring here, the double, single, double conjugated system is locked in the S-cis conformation. Again, if you look from double to double, you can see that cis geometry around the single bond. And again, the ring locks our diene in that S-cis conformation. So that will be a very good Diels-Alder diene because it will always be in that S-cis. The other one will never be in the S-cis, so it won't work. So something like this, where we have, say, methyl groups that are cis on our diene, you'll notice that when we put our diene in the S-cis conformation, those methyl groups collide with each other, which means that this molecule will not exist in the S-cis conformation very long. It will spend most of its time swung around in the S-trans in order to minimize the collision between these methyl groups. So it might be a suitable reaction partner in our Diels-Alder reaction, but only rarely will it actually find itself in the S-cis ready to react. If we make those double bonds trans instead, you'll notice that we move the methyl groups out of the way of each other and only place the hydrogens in the way of each other. So that will be a little bit better. This is a lot more like butadiene. These methyls are ostensibly not there as far as the equilibrium of the S-cis to S-trans rotation is concerned. So that will be a little bit better because we minimize that collision. Here again, we minimize it even more. And here again, we minimize it the most. So all we need is a diene that can have an S-cis conformation. That's the only requirement for the diene. Another outcome of the stereochemistry of the Diels-Alder reaction is that the product will always be syn. Notice that as the diene approaches the dienophile, in this case they're using two cyclopentadiene rings, one being the diene, one being the dienophile, but as one approaches the other, notice that one has to approach from either the bottom or the top of that ring. And since it's a concerted reaction, all of those bonds are formed and broken simultaneously, which means that when those bonds finally get formed, these hydrogens will always be pointing in the same direction. you'll always have them approaching from the same face, pointing in the same direction as each other as the reaction proceeds, which means that once all of our bonds are broken and formed, those H's will always be syn. That is a requirement for Diels-Alder reactions. The concerted nature of the Diels-Alder reaction ensures that the stereochemistry will be syn. Remember when we've looked at mechanisms, generally speaking, mechanisms that occur in two steps end up being anti or trans, and reactions that occur in one step end up being syn. Remember the hydroboration oxidation was syn, and the osmium tetroxide formation of diols was syn, whereas the bromination of an alkene going through the bromonium intermediate was trans, or ring opening an epoxide, which goes to the epoxide intermediate, is trans. So single step mechanisms will almost always be cis. That is also true for the Diels-Alder reaction. Another stereochemical requirement of the Diels-Alder reaction is something we call the endo rule. And that basically means that the dienophile, in this case, since the green molecule here has a withdrawing group on it, that will be the dienophile. The dienophile will approach the diene with any of its pi bonding constituents endo or underneath the diene rather than exo, away from the diene. So notice here we've got two ways that our carbon-carbon double bond on our dienophile can approach the diene. We can have it approach the diene with the carbonyl away from the diene, so on the other side from the diene, or we can have the dienophile approach the ring with the pi bond withdrawing group coming towards or underneath the diene. That is called endo, where the withdrawing group approaches from underneath the ring. The reason that happens is because there is a favorable interaction between the withdrawing pi group and the electron-rich pi bond that eventually gets formed when we do our reaction. So these two groups will tend to tether to one another. They won't bond, but they will tether, kind of hold on to one another. And that ensures that we get the specific stereochemistry at this carbon. Notice that the stereochemistry at this carbon has the H kind of going up and out, and the carbonyl aldehyde kind of going down and in. The other approach, if we have exo approach, you'll have the other stereochemistry there. You'll have the aldehyde away, and you'll have the hydrogen endo. So the rule is that anytime our dienophile has a withdrawing group like that, the endo product will predominate. You will get exclusively, or maybe say 90% endo and very little, or up to maybe 10% exo. But generally speaking, we expect the endo to be the major product. I have a very thorough Diels-Alder reaction stereochemistry summary on Canvas. It used to be called Moodle, now it's called Canvas. So I encourage you to check that out, read through that, and try to understand the difference between endo and exo, as well as some geometrical requirements relating to whether the double bonds involved in the diene or the dienophile are cis or trans. There's a lot to take in there, so certainly take a look at that, please. So let's look at why the pericyclic reaction is an interesting reaction and why it is classified as a reaction of aromatic compounds. It fits into the same overarching scheme that looks at molecular orbitals like we looked at for conjugated systems. Here is a diene, 1,3-butadiene, and a dienophile. In this case, they're just using ethene. Even though ethene doesn't have a withdrawing group, it can still act as a dienophile. We won't get as good of a reaction, as fast as a reaction, because the dienophile is not being withdrawn by that withdrawing group. But we can still use it as a dienophile along with the diene in the reaction. So in order for these reactions to work, we have to have appropriate overlap between the end carbons of the diene and the two carbons involved in the dienophile. Now, since the diene acts as the nucleophile in this reaction, we are looking at the HOMO of the butadiene. We're going to use the highest electrons, highest energy electrons from the highest occupied molecular orbital as our nucleophile electrons. We also will then use the LUMO from ethylene as the electrons into which the nucleophile will donate. So the LUMO from the dienophile and the HOMO from the diene. Let's look at what that looks like. Again, if you go back and look at the molecular orbital picture for butadiene, the HOMO, the second molecular orbital in this case for butadiene, looks like this. We've got bonding character between carbons 1 and 2, anti-bonding character between carbons 2 and 3, and bonding character between carbons 3 and 4. That's the HOMO of butadiene. Our LUMO of ethylene, or ethene, will have the lobes out of phase. There are two molecular orbitals for ethylene. One of them has the two lobes in phase. The other has the two lobes out of phase. The LUMO will have them out of phase. So you'll notice that when we match up the end electrons, so you'll notice that when we line up the end carbons, as long as one of these, the HOMO or the LUMO, approaches from the top or the bottom, we will get overlap constructively between the lobes. You'll notice that in this case, if the LUMO approaches from the bottom or the HOMO approaches from the top, the negative lobes overlap on those end carbons. We get bonding character there. And here, these lobes overlap as long as one approaches from the top. We could of course have the ethylene approach from the top, in which case this green negative would overlap with that green negative, and this blue positive would overlap with that blue positive. Either way, you get overlap between the end carbons of the butadiene and the end carbons of the ethylene. That allows the reaction to work. That's why a 4+2 reaction works. But let's look at a 2+2. Now, instead of a 4+2, we're just going to use, say, 2 ethylenes. So this would be called a 2+2 cycloaddition. Notice that we can kind of write the same mechanism. If we take the pi electrons from our nucleophile, donate them into our electrophile, and then have the electrophile's electrons come back, donate back into the nucleophile, very similar mechanism for the 4+2, in this case for a 2+2. That will get us a transition state where the pi bonds are being broken, the new sigma bonds are being formed, and instead of making a 6-membered ring in the 4+2, we make a 4-membered ring in the 2+2. But let's look at why this actually does not work. We can write a mechanism for it. It looks perfectly valid. We're not breaking any rules here as far as Lewis structures go. But in order for this reaction to work, we need the HOMO and LUMO carbons to line up. So let's take one of these ethylenes and look at its HOMO. The HOMO of ethylene has both of the electron lobes in phase. And then we'll also look at the LUMO for the other one. So one of these will be the nucleophile. We look at the HOMO for that. The other one will be an electrophile. We'll look at the LUMO for that. LUMO for ethylene has the lobes out of phase. So you'll notice that one pair of carbons lines up. The left carbons, in this case, the left carbon on the HOMO aligns with the left carbon on the LUMO. So that works. That will get us a bond there. But the other carbon lobes do not interact. They are anti-bonding. They are out of phase. What that means is that a 2+2 cycloaddition is forbidden in the ground state. As long as we have an empty LUMO and a full HOMO, the ground state, that is to say, forbids a 2+2 cycloaddition. It does not work. But it turns out that you can induce photochemically 2+2 cycloadditions, meaning that if our HOMO absorbs a photon of light, that causes one of its electrons to jump up into a higher orbital, then you can get a 2+2 cycloaddition. Here's what I mean by that. So here's our normal picture of two ethylenes. Or you think of it as the ethylene HOMO and the ethylene LUMO. Now, the normal case would be that that would not work. The positive lobe and the positive lobe interact here, but they do not interact here. That's why in the ground state, ethylenes will not react with each other in a 2+2. But if we take one of these electrons from the HOMO and excite it into the LUMO picture doesn't change. Notice that the lobes are the same. It's still the same orbital, but now it's occupied. It is half occupied, singly occupied. So it's not a LUMO anymore. It's not unoccupied. What we call it now is a HOMO star, meaning it's now a HOMO. It is the highest occupied molecular orbital, but it's not the ground state HOMO. It's an excited state HOMO. So now what we can do is we can take the HOMO star, which is populated, and use that as our HOMO. And then we'll take an empty LUMO from another molecule, and now you notice that all of our lobes line up. The HOMO star looks like the LUMO. Notice that these look like the same orbital, except that the HOMO star is populated. So it can act as the nucleophile. The LUMO has to act as the electrophile. Basically, the difference is that this turns into a single electron reaction. It moves a radical around rather than moving a pair of electrons around. But we get positive reinforcement of these orbitals on the left side, plus and plus. We also get positive reinforcement of these orbitals, these waves, on the right, negative, negative. That means that 2+2 cycloadditions, despite being thermodynamically forbidden, meaning forbidden based on the ground state, they are photochemically allowed. They are allowed in the excited state. And 4+2 is the other way around. 4+2 worked when we used the ground state. But go back and try to figure out what a 4+2 would look like if we used the photochemically excited state, if we used the HOMO star of butadiene as our HOMO. And you'll notice that a 4+2 will not work in this photochemical setup. We'll also use some class time to look at 6+2s, and we'll be able to conclude whether a 6+2 would be thermodynamically allowed or if it would be photochemically allowed. It's always going to be one or the other. So we'll take a look in class. For now, that's all for the Diels-Alder reaction. So go back and look at the Diels-Alder stereochemistry summary and make sure you understand how to draw these orbital pictures and make sure you understand the difference between a photochemical and a thermodynamic Diels-Alder. Moving along to our electrophilic aromatic substitution section. Remember, this is kind of the bulk of this chapter. I wanted to show you kind of a fun picture. This is a photo that was taken from the Yale Sheffield Scientific School, which eventually became the Graduate School of Arts and Sciences at Yale. This was the chemistry class of 1898, and it's kind of a fun picture to look at. Everybody's kind of showcasing the tools of their trade. This guy's got a big round bottom flask. They've got some of their chemicals out here, this little stockroom drawer full of chemicals. We've got a giant weighing scale. Kind of a fun picture, a lot going on. But there's a little hidden joke here. You see right here, there's this little plaque, this little box, and it's got something written on it. If you zoom in, it says hot or cold, oh no. Now, this is clearly some kind of an inside joke, but what it appears to reference is nitric acid, HONO, which is a common reactant that's used in a electrophilic aromatic substitution reaction. And the reason that I believe that this is a reference to that is that this electrophilic aromatic substitution, and in general, these reactions of aromatic compounds, are one of the oldest classes of reactions that were studied by organic chemists. This chemistry that we're going to learn in this chapter would have been cutting edge chemistry around the beginning of the 1900s. So this is an old field of chemistry, and what I'm guessing is that these guys were studying these reactions, and this is an inside joke about this reactant, nitrous acid, that converts an amino group on an aromatic ring into a diazo group on an aromatic ring. This building, I checked, no longer exists. It's been knocked down and rebuilt with something else. Okay, so here's the big picture on electrophilic aromatic substitution. The big picture for this reaction is we take an aromatic ring, we add to it a strong electrophile in one step, and in a second step, we follow up with a base. And the result is that the electrophile is substituted on the ring in place of a hydrogen. You'll notice that this carbon right here has one hydrogen on the reactant, and in the product, that hydrogen has been replaced with the electrophile. So this is not a nucleophilic substitution. It's not like an SN2. There's no nucleophile that's adding to this ring and displacing a leaving group. Instead, it's an electrophile that is substituting that hydrogen, but it's doing so in a different type of mechanism. If it was the same mechanism as SN2, we'd call it SN2. So here's the mechanism. The ring in this reaction acts as the nucleophile, the same way that in the Diels-Alder reaction, the conjugated diene acted as the nucleophile. Here, the conjugated, in fact, aromatic ring acts as the nucleophile, and it uses one of its pi electron pairs to attack the electrophile. That will add the electrophile to one of the carbons on that ring, and it will leave a positive charge on the neighboring carbon, that carbon that lost its pi bond. And because this is a highly conjugated system, that positive charge will be delocalized throughout that ring. We call this an rhenium ion, or sometimes it's called a sigma complex. Now, this is no longer an aromatic molecule. This sigma complex, a rhenium ion, is not aromatic because by using one of these pi electron pairs to make a bond to the electrophile, we break that aromatic cycle. The carbon that gets the electrophile no longer has any pi bonds on it, no longer has any p orbitals on it. So we break that conjugation. But it is resonance stabilized, so it's at least tolerable. But in the next step, what happens is the base removes the hydrogen from the carbon that got the electrophile. Those electrons then fall back in to make a pi bond. That's kind of like the second step of an E1. And we regenerate our pi bond, we regenerate our aromatic system, but now we have put the electrophile on the carbon that eventually lost its hydrogen. So this is different from our electrophilic addition, where we say added hydrogen and bromide, HBr, across a pi bond. It's different because in electrophilic addition, first we added a hydrogen, and that gave us a positive charge. But then the nucleophile, like a bromide, for example, would come in and attack that carbocation, and we would add the H and the Br across the double bond. In the electrophilic addition, we use up the pi bond to add two groups across it. In this case, we use the pi bond to make the bond to the electrophile, then we remove a hydrogen to remake the bond. So it's different from electrophilic addition. Also, we need a very strong electrophile. We need an electrophile with a full or nearly full positive charge. Why would that be? Well, in order to convince the ring to give up a pair of pi electrons and therefore lose its aromaticity, this electrophile needs to be really, really, really attractive to the ring. This ring is not a particularly great nucleophile because it really doesn't want to give up its electrons. By giving it up its electrons, it becomes non-aromatic. So we need a really attractive, really strong electrophile in order to convince the ring to give up those electrons. So one task that you'll need in order to learn this material is basically to learn what the recipes are to generate an appropriate electrophile for the ring. For example, if we want to add a bromine to our ring, we need essentially what is Br+. So the question would be then, how do we generate Br+? What is the recipe for our reagents to generate a Br+? Well, to get a Br+, what we use is Br2 bromine along with FeBr3. FeBr3 is a very strong Lewis acid. Transition metals like iron very readily accept lone pairs. That's what a Lewis acid is. That's why metals, which tend to be positive charges, like to accept electrons. That makes them good Lewis acids. So when we mix Br2 with FeBr3, what happens is the Br2 will donate electrons to the FeBr3, and that will make what is basically Br2 complex with FeBr3, or FeBr5. It would kind of look like this. It's got a Br2 that's complex with the FeBr3. That gives one of the bromines 2 bonds, and therefore a positive charge, and it gives iron an extra bond, which gives it a negative charge. So now what happens is the ring will add to one of these bromines and displace the FeBr4-, basically returning the electrons to the Br+ and making it just bromine. So that puts our bromine on the ring. It gives us the rhenium ion, just like the E+ we saw in the other slide gave us that rhenium ion. Then the base is basically bromide. We've got FeBr4 floating around. That bromide can grab one of our hydrogens. Again, it's going to be the hydrogen that is bonded to the carbon that got the bromine. We'll return those electrons back to the ring, give them the aromatic system back, and now we've made HBr, and we've regenerated FeBr3. We started with FeBr3, it got consumed in the course of the reaction, and got regenerated at the end. Therefore, FeBr3 is a catalyst. So remember that the recipe to add a bromine to the ring is Br2 and FeBr3. All other reagents will basically follow the same mechanism once they generate the electrophile. If you want to add a chlorine to the ring, the question is, how do we make a chlorine plus? Well, you do it similarly to the way we made a Br+. You use Cl2 instead of Br2, obviously, but then we'll use aluminum trichloride, which is analogous Lewis acid to FeBr3. Instead of FeBr3, it's AlCl3, but it works the exact same way. The chlorine complexes to the aluminum. That ring then adds to the complex, adds the chlorine, then that gives us AlCl4. The chloride comes back, grabs the H, regenerates our aromatic system, and now we have HCl and regenerate our AlCl3 catalyst. For iodine, the recipe to add iodine is a little bit different. In order to make the I+, we need I2 and twice the stoichiometric amount of nitric acid. So our ring plus I2 plus HNO3 will generate an I+, and that will go onto the ring. We can add a nitro group to make nitrobenzene. NO2 is called a nitro group. We can add nitro group by using nitric acid and sulfuric acid, HNO3 and H2SO4. What these two things basically do, here's nitric acid, HNO3, here's sulfuric acid, H2SO4. It turns out that sulfuric acid is a stronger acid than nitric acid. So when we combine the two, the sulfuric acid acts as the acid, the nitric acid acts as a base. The nitric acid will grab an H from the sulfuric acid. That makes this protonated form of nitric acid, which then collapses, it decomposes, kicks off water here, and makes NO2 plus. That's called nitronium, and that's NO2 that gets added to our ring. So again, in all of these mechanisms, the entity that gets added to the ring needs to have a positive form. It's NO2 plus. These recipes make I plus. This recipe makes Cl plus. Our previous recipe made Br plus. Some other transformations that we can do. Here's a ring, an alkyl benzene. We can add nitric acid and H2SO4 to add the nitro group. We just saw that. We can then convert the nitro group on the ring into an amine using a metal like zinc, tin, or iron, along with aqueous hydrochloric acid. That conversion works on the aromatic ring. We can also add this sulfonic acid group, this SO3H group. We can do that by using SO3 and H2SO4. It's a similar reaction like we saw for adding the NO2 group, adding the nitro group. We generate an SO3H electrophile, and that goes on the ring. That's commonly done in industry, in industrial processes, because if you deprotonate this benzene sulfonic acid, you get an alkyl benzene sulfonate, and that is what a soap is. That's a detergent. So this is how they make soap. This SO3H group is also extremely useful because it can be easily removed from the ring as well. You can put it on pretty easily using SO3 and H2SO4. You can also take it off using water, acid, and heat. The benzene sulfonic acid will turn back into benzene, basically substituting the H in place of an SO3H, and that'll get us back to benzene. These are useful, as I'll show you at the end of the lecture, as what we call a blocking group. We can put it on the ring and do something else with the ring. With the SO3H will block that position on the ring. Then when we're done with our transformations, we just remove the SO3 and we're back to where we want to be. I'll show you a strategy for that a little bit later. We can add alkyl groups to the ring in a method called a Friedel-Crafts alkylation. The way it works is we start with, again, an aromatic ring. That's what we need. Then what we need is an electrophile. If we want to add an alkyl group, we basically need an R+. The way we make the R+ is with Rx, a halogen like chlorine, bromine, and iodine, and a strong Lewis acid. Usually we match the Lewis acid to the halogen. So if we're using chlorine as RCl, we'll use AlCl3 as our Lewis acid. If we're using bromine as RBr, we'll use FeBr3 as our Lewis acid. That combination basically makes R+, and that will go on the ring. As an example, here's tert-butyl chloride. Since we're using RCl, we're going to use AlCl3. Notice that the carbon that bears the chlorine is the carbon that gets attached to the ring. The carbon that bears the chlorine is the carbon that ends up getting the positive charge, and so that is the site of attachment. Very convenient way to add alkyl groups onto an aromatic ring. Now, there are some problems with Friedel-Crafts alkylation. The first is that it only works with benzene. There are other types of aromatic rings that we're going to see. For example, furan is an aromatic ring, pyrrole is an aromatic ring, pyridine is an aromatic ring, but the Friedel-Crafts alkylation will only work on benzene. Another problem is that rearrangements often occur. In the Friedel-Crafts alkylation, we generate essentially, again, an R+. The chlorine adds to the aluminum, and that basically generates a C+ on the carbon that had the chlorine. it's that cation that then the ring adds to get our sigma complex, our rhenium ion. So the problem is that if you make a primary carbocation starting from a primary halogen, that primary carbocation is very likely to rearrange, undergo a methyl shift or a hydride shift to get us a more stable cation. And it is that cation that will eventually add to the ring. So if you try to add a propyl group, starting with propyl chloride, you're very likely to end up with the isopropyl group, the rearranged propyl group, on the ring. Secondly, the alkylated product, meaning the product of the reaction with the alkyl group on the ring, is more reactive towards further alkylation than the original ring was. That means that we end up getting multiply alkylated benzenes. Let's imagine this for a moment. We've got benzene floating around in our reaction mixture and AlCl3 and our tert-butyl chloride. The tert-butyl chloride will react with the AlCl3. That give us a tert-butyl cation that adds to the ring and get us tert-butyl benzene. What I'm saying here is that the tert-butyl benzenes in our mixture are more reactive to subsequent reactions than benzene is. So if we've got benzene floating around and tert-butyl benzene floating around in our reaction, it's the tert-butyl benzenes that are going to be more reactive towards our tert-butyl chloride and AlCl3. That means that we're going to end up with some benzenes that got no reaction and some benzenes that get 2 or 3 tert-butyl groups added to the ring. The product is more reactive towards subsequent reactions than the benzene ring is to begin with. So let's take a few minutes and look at why this is. This is going to be a fairly in-depth analysis of why an alkylated benzene is more reactive than a regular benzene. It's a very important aspect of electrophilic aromatic substitution that makes that true. So let's look at, for example, the nitration of phenol. Remember, phenol is another name for hydroxybenzene. It's a phenyl alcohol. We call it phenol. The recipe for nitration is HNO3 and H2SO4. Remember, that is the recipe that puts a nitro group on our ring. Now, since the phenol group, that OH alcohol, is already on this ring, that means that there are 3 possible places that the nitro group could add. It can add to the carbon adjacent to the alcohol carbon, or 2 away from the alcohol carbon, or 3 away, 1, 2, 3 away from the alcohol carbon. Now, just for nomenclature's sake, we call this in the 1-2 arrangement the ortho product, or we call that the ortho position. This 1-3 arrangement we call meta, or we call that the meta position. And this 1-4 arrangement, we call it para, or we call that the para position. It's basically a relative position of one group to the other. So we'd say these are ortho to each other, these are meta to each other, these are para to each other. Or we would say that the nitro goes in the ortho position, or the nitro goes in the meta position, or the nitro group goes on the para position. Now, just based on statistics, if we were to naively assume that everything in chemistry occurs based on statistics, notice that there are 2 ortho positions that will give us our ortho product, 2 meta positions that will give us our meta product, and 1 para position that would get us our para product. So if we were naive, we would assume that we'd get 40% ortho, 40% meta, and 20% para, just based on statistics. However, in real life, when we do this reaction, we end up with 67% para, 31% ortho, and only 2% meta. So there's something really interesting going on here. That means that despite the fact that we only have one para-hydrogen, it's almost always that para-hydrogen that reacts. Similarly, there's something really bad about the meta position. Even though we've got the same number of meta and ortho hydrogens, it's always between those two, the ortho that reacts, never the meta. So let's try to figure out why the para is so good and the meta is so bad. And eventually we'll be able to explain that problem with the Friedel-Crafts alkylation. Trust me, it seems like a roundabout way to get to it, but at the end it will make sense. There is a chemical origin to the specificity of this reaction. This is not just statistics. There is something chemical that is making para very good and making meta very bad. To understand this, we need to consider three factors. The first, we can look at the reactivity of the starting material. Second, we can look at the stability or perhaps the lack of stability of any intermediates. For example, that arenium ion, that sigma complex. We can look at how stable or unstable that is. And lastly, we can look at the stability or lack thereof of the products. Let's start by looking at the reactivity of the starting material. Let's look at what the OH group does to the phenol's reactivity. What I'm going to do is I'm going to take a lone pair off of this oxygen and I'm going to start moving it through the ring. I'm going to make a pi bond here, and that displaces this pi bond onto the orthocarbon. Then I'm going to take that electron pair, move it back down here to make a new pi bond. That's going to put this pi bond onto the para position. Then I'm going to take these electrons, move it back down to make a new pi bond, push these electrons from the pi bond onto that carbon. That's the other ortho position. These are second order resonance structures. They're minor, of course. Out of these four pictures, the best one is going to be the neutral phenol. But the fact that we can draw valid resonance structures like this tells us that there should be more electron density on the carbons that bear the negative charge. Now, if you are astute, you'll notice that those positions, the carbons that bear the negative charge, are the ortho and the para positions. And if we go back and look at our slide, it was the ortho and the para positions that got the bulk of our reaction. The meta was only 2%. So between the ortho and the para, that accounted for 98% of our products. And it turns out that with phenol as our reactant, those are the sites that actually have negative character. Again, this kind of shows what the composite of all these pictures is. There's some neutral oxygen, but there's also some positive charge on the oxygen. There's neutral carbons, but there's also negative character on the ortho and the para. What this means is that electron density and therefore nucleophilicity is increased at the ortho and para carbons as a result of pi donation by the OH group. What I mean by pi donation is the electrons are being donated from the OH into the pi system. It's not going through the sigma system. It's only the pi bonds that are being moved around. So we call that pi donation from the OH group. And that increases nucleophilicity at the ortho and para positions. Remember that in this reaction, it's the ring that's the nucleophile. So that makes the ortho and para positions more nucleophilic. Again, here's an electron potential map that kind of mirrors this. This is actually phenoxide, but most of our electron density is going to be on the O because that's where our lone pairs are going to be most of the time. But we've got some negative character on the ortho and the para positions. Okay, so that explains some of, or at least part of, the preference for acting on the ortho and the para positions. Simply looking at what the reactant looks like. Let's now, rather than looking at the reactant or the starting material, let's consider the stability or lack thereof of any intermediates. Specifically, we're going to look at the rhenium ion. So let's imagine the nucleophile, our phenol, adding to the nitro group from the ortho position. So we're going to call that ortho attack, or meta attack, or para attack. So adding the nitro to the ortho position, adding the nitro to the meta position, and to the para position. Just looking at these intermediates, without even looking closely, you can see that we get 4 resonance structures from the ortho attack, and we get 4 resonance structures from the para attack, but we only get 3 resonance structures from the meta attack. That means that since more resonance means more stability, that you get a more stable intermediate if you go ortho position attack or if you go para position attack. If you're paying very close attention, the extra resonance structure in the ortho and the para comes right here. This very first structure that I'm showing you on the ortho and the second structure that I'm showing you on the para. Notice that in the course of moving our positive charge around from the, let's say, first position to the third position to the fifth position, we get 1 positive charge on that first position, and that can be cured by donating electrons from the oxygen. That gets us this intermediate. Same thing here. We end up with a positive charge on the carbon bearing the oxygen. We can take electrons down from that, and that gets us a new intermediate, this guy right here. Notice that in the meta pathway, we never end up with a positive charge on the OH carbon. So we can't generate that 4th resonance structure. Another thing to pay attention to is that this additional resonance structure that we get is the best of the 4 because it has all of its atoms with octets. In all of these other 3, this one here for ortho, that one there for ortho, and that one there for ortho, we've got a positive carbon. And a positive carbon only has 3 bonds and no lone pairs. So 1, 2, 3 of these are missing an octet. 1, 2, 3 of these are missing the octet in the para, but we've got 1 in the para that has an octet and 1 in the ortho that has an octet. In the meta, we have no structures that have all their octets. All 3 of these have positive carbons, so they are missing their octet on that carbon. So, addition to the ortho or para carbons provides a 4th exceedingly stable resonance contributor, again, via pi donation. So this one here, that with the bracket, and this one here with the bracket, these are extra good. So we've explained now, based on the starting material reactivity, why ortho-para is favored, and based on the stability of the rhenium ion, why ortho-para is favored. Now, we call this OH group an ortho-para director because when it is on the ring, it will direct any electrophiles onto the ortho or para positions. Again, without knowing about any influence, we'd expect 40 ortho, 40 meta, and 20 para. But because the OH is an ortho-para director, we get 31% ortho, 67% para. It makes the orthoparasites more reactive and gives resulting stability to the rhenium ion by adding the nitro group to those positions. Here are some other ortho-para directors. We saw that OH already was a good ortho-para director. N, say NR2 or NH2, is a better ortho-para director because nitrogen with that lone pair is more willing to donate its electrons into the ring. Nitrogen is less electronegative than O. So between an N with a lone pair and an O with a lone pair, the nitrogen is more willing to donate the electrons in. That gives us more negative character on the ortho and para positions. Even better than an N neutral with a lone pair would be an O minus with 3 lone pairs and a negative charge. That's even better because it's going to be more willing to donate its electrons in. OH and OR are very similar. This guy's kind of interesting. He's a nitrogen with a lone pair. And of course, that nitrogen could donate his lone pair into the ring. But we could also take the electrons away from the ring. This carbonyl, notice, is a withdrawing group. It can take the electrons towards itself and towards the oxygen. And in doing so, you end up with a resonance structure where there are no lone pairs on the nitrogen. So now in this picture, the nitrogen cannot donate electrons into the ring. So this is one of the worst ortho-pair directors. It still is an ortho-pair director, but it's not a very good one because those electrons spend some of the time delocalized through this other pi system, not delocalized through the ring. This order here from O minus to N to O and O to OH and OR to N with a carbonyl, this is roughly related to increasing lone pair or HOMO energy. The higher the energy of these lone pairs or the higher the energy of the HOMO, the more willing these are going to be to donate those electrons. Now, I put something over here. Notice that this is an alkylated benzene, which was the product of our Friedel-Crafts alkylation. Now, because the R group does not have any lone pairs on it, it can't be a pi donor. So it can't do the same thing that these other groups can and donate electrons in and increase the negative charge on the orthopara, etc., etc., etc. But it still is an orthopara director. Let me show you why. Along with this pi donating capability, of course, becomes increasing orthopara directing capability. We've got this R group with no pi electrons, but it still is an orthopara director despite not being a pi donor. There's no pi electrons to donate. So, turns out that it is indeed an orthopara director. If we have this methyl group on our benzene and we try to do a nitration, it's going to favor ortho 60% and para 36%. Now again, this is interesting because this is the opposite pattern. We saw before that it was roughly double para from ortho. That's different from methyl, and I'm going to tell you why in a minute. But for now, we can observe that a methyl group is indeed an ortho-pair director. It does not allow things to go meta. So let's look at the stability or lack thereof for the rhenium ion when an alkyl group is on the ring. Remember that because the alkyl group is not a pi donor, it makes no sense to look at the reactivity of the starting material. It's not going to be able to increase the negative character on the ortho or para positions because it has no electrons to donate. But if we look at this, first of all, notice that we get equal number of resonance structures from ortho attack, meta attack, and para attack. So there's even less preference than there was before for ortho and para when there's a methyl group. But look at this. In the meta pathway, all of our cations there, and there are secondary. But when we look at the ortho or the para, here's a secondary, but here's a tertiary. Why do we get a tertiary? Because there's a methyl group there. The methyl group that we called our ortho-para director turns this cation into a tertiary one. Same thing in our ortho pathway. Here's a secondary, but we get another resonance structure that is tertiary, and it is only tertiary because of our methyl group. So the methyl group or an alkyl group in general is ortho-para directing because it gives us a more stable cation in the ortho and para pathways than it does in the meta pathway. We call that sigma donating. What do we mean by sigma donating? Remember, the reason that the tertiary is better than the secondary is because of hyperconjugation. Hyperconjugation is donation of electrons through a sigma bond system. If you don't remember, go back and look at our free radical chain reaction chapter in the book. I believe it's chapter 4 in Wade. And you will find that hyperconjugation is what makes tertiary cations better than secondary and secondaries better than primaries. And it is because of overlap of sigma bond systems, not pi bond systems. So alkyl groups are sigma donating and makes them ortho and para directors. It's the stability of the rhenium ion. Again, we've got tertiary carbocations there. So addition of the ortho or para carbons provides a resonance structure with a more stable tertiary cation. Okay, now I mentioned that with the methyl group, we got more ortho and less para than we did with the OH group. Here's our OH group. With our OH group, we got more para than we did ortho. What this means is that the product distribution is closer to the statistical values. Notice that we've got twice the number of ortho positions than we have para positions. So the origin of this 60 to 36 ratio is based more on the statistical values and less chemical influence. So there's two reasons why ortho is favored over para. The first is just based on statistics. There's 2 ortho positions and only 1 para position. But that didn't matter when it was an OH group. It only mattered when there was a methyl group on there. So it turns out that because methyl is small, it does not block the ortho positions in the same way that larger groups do. The OH is big enough that it kind of blocks off that ortho position. So if we look at our ortho and para pathways for the OH group, they were both equal. The intermediates were equal for the ortho and para pathways. Of course, it turned out that there were more orthos than para, so the explanation for why para is still better than ortho when their pathways are equivalent, and there's actually twice as many orthos than para, is that the group, the OH group itself, blocks some of that access to our 2 orthos. So basically, for any group bigger than methyl, para is favored over ortho. Sometimes it can be as great as 2 to 1. But when we have something methyl or smaller, there's not much smaller than methyl. When we have something methyl or smaller, we start to get back to our expected statistical ratio because the pathways are equivalent, but there's twice as many orthos than para, and the orthos are no longer being blocked. So you can see that with a methyl, we have 60 to 36 ortho to para. If we go back to ethyl, it flips around again. We go back to predominantly para, again because the ethyl group blocks addition to the ortho positions, and therefore we mostly get para. So let's summarize the directing effects of ortho-para directors. We said that ortho-para directors are electron donating groups, meaning an electron donating group on a ring will be an ortho-para director. Now, specifically, pi donating groups, which are groups with lone pairs of electrons on the ring bonded atom, will generate secondary resonance structures that increase electron density at the ortho and para positions. Those tend to be the strongest ortho-para directors. Remember, we said O- or N with a lone pair. Those were good ortho-para directors. Pi donating groups also give us a 4th resonance structure in the rhenium ion that is octet satisfied and therefore extra stable, lowers the energy of the intermediate. Sigma donating groups, which are basically alkyl groups, they stabilize the rhenium ion by hyperconjugation, not by increasing the number of resonance structures. And that's a less dramatic effect. So sigma donators are not as good ortho-pair directors as pi donators are. And lastly, steric factors, factors based on bulkiness or size of groups, steric factors will favor para addition for anything larger than a methyl group. Okay, so if pi donators or sigma donators are ortho-para directors, what do you think withdrawing groups are going to be? Well, let's look at a nitro group on the ring. When we have a nitro group on the ring, say instead of an OH or instead of a methyl or an alkyl group, nitro looks like this. It's an N plus with a double bond O and an O minus. That's a neutral group. It's chemically neutral, but the nitrogen on the ring has a positive charge. When we try to do a nitration on a ring with a withdrawing group on it, say put a nitro group on the ring, notice what we get. We get meta direction. The ortho and para are almost entirely unformed. That means that withdrawing groups that can withdraw electrons out of the ring due to having a positive charge on the group itself is now a meta director. Let's go through and observe the same effects that we did for ortho-para directors, but now do it for meta directors. So let's look at our secondary resonance structures. Remember how with ortho-para directors, they had lone pairs on the ring bonded atom, and that was able to donate electrons into the ring. Since the nitrogen has a positive charge, it will pull electron density out of the ring. So we'll take these electrons, move it onto the N, and then take the N's double bond O, electrons, move those electrons onto the O, we get an O minus. We could then start moving these pi electrons around. Move these pi electrons to its neighbor, that delocalizes the positive charge to the para position. This pi electron comes down here and delocalizes the positive charge onto the other ortho position. Now, what does our composite look like? We've got positive character on the ortho and para positions. Remember that before, we had negative character on the ortho para positions. So the sites on the ring that are going to be the most nucleophilic now are the meta positions. Those are the sites on our ring with the most electron density. So the ortho-para positions now lack any nucleophilic character due to pi withdrawal. Again, this is a pi withdrawing group. It's withdrawing electrons through the pi system. It's kind of interesting to note that the reason that ortho-para directors were ortho-para directors was because they made the ortho-para positions better. The reason a meta director is a meta director is not because it makes the meta positions better, but because it makes the ortho-para positions worse. It's always the ortho-para positions that are affected by a group on the ring. It's just whether it makes them more nucleophilic, as in the case for ortho-para directors, or less nucleophilic, as in the case for meta directors. Now let's look at the effect on the rhenium ion. So again, if we look at ortho attack, which we know is not going to happen, we've already seen why, and para attack, which we know is not going to happen, versus meta attack, first of all, notice that these are all 3 resonance structure intermediates, 3 resonance structures in either case. But in the ortho position, look what we have. When we add a group to the ortho position, we end up with a resonance structure with a positive charge next to a positive charge. And that's really bad. We also get that in the para position. When we add the para position, we end up with a resonance structure with a positive charge next to a positive charge. Recall that when we had a ortho-pair director, that positive charge on that carbon, the carbon bearing our group, gave us that fourth resonance structure. Now this resonance structure is extra bad. But in the meta pathway, we never end up with a positive charge on the carbon bearing our nitrogen. So we don't have any extra bad structures here. Remember, this meant that we didn't have any extra good structures when we had a donating group. So in the presence of an electron withdrawing group, the ortho and para carbons get unfavorable resonance structures, and therefore meta is favored. Meta does not generate any unfavorable resonance structures, making it the best pathway. So again, it's not so much that the meta pathway is extra good, it's that now the ortho-para pathways are extra bad. So let's look at some other groups that are meta-directors. Again, all of these groups, anything that is a meta-director, should in some way be electron withdrawing. So here we have some groups ordered in order of electron withdrawing character. We've got the NO2. We've already seen what NO2 looks like. NO2 has an N plus on the ring. Here's SO3H. That looks like this, SO3H. That's got an S plus on the ring. Here's CN. Now CN triple bond is neutral, but there's a resonance structure. If we take one of these pi bonds and move them on to the nitrogen as a lone pair, we get N minus and C plus. A quaternary ammonium group has a positive charge on the N, the same way that the nitro group has a positive N. And a carbonyl can also be a withdrawing group, because if we draw a resonance structure, take the pi electrons, move them onto the oxygen, that gets an O minus and a C plus. So now our carbon has partially positive character. Notice that in all of these structures down here, the atom bonded to the ring has either full positive character on the N, on the S, on the N, or partially positive character on the C here or the C here. So what about halogens? Halogens, because they have lone pairs on them, are weakly pi donating. They are still pi donating, but since they're so electronegative, they really don't like to give up those pi electrons. So they're weakly pi donating. But they are sigma withdrawing because they're so electronegative. So that means that we end up, first of all, with negative character on the ortho and para positions. That makes them ortho-para directors. But look at here. When we add ortho or para, we get a couple resonance structures that put the positive charge next to the chlorine. Here, positive next to a chlorine, and here, positive next to a chlorine. So those are extra bad because this carbon is already electron deficient. It does not want an atom pulling more electron density away from it. So we get a bad intermediate here and a bad intermediate here. The net effect of this is that they are weak ortho-pair directors. They are ortho-pair directors, but they decrease the EAS reactivity overall, the reactivity of electrophilic aromatic substitution. Now, what do I mean by that? So far we've talked about directing effects. We've talked about how groups on the ring will donate or withdraw electrons to change where additional groups go. But we haven't talked yet about reactivity overall. Remember that the ring is the nucleophile. So anything that increases electron density in the ring will make the ring more reactive. That means that ortho-para directors, which are pi donors, will increase the ring. We call them activating groups. They make the ring more reactive. So OH, O minus, NH, OR, alkyl groups are donating groups and they are activators. They make the ring a better nucleophile. On the other hand, these withdrawing groups, these meta directors, they take electron density out of the ring, which will make the ring a poorer nucleophile. And so we call them deactivating groups. So ortho-pair directors are activating groups. Meta directors are deactivating groups. The halogens are somewhere in between. They are ortho-pair directors, but they are deactivating groups. They're right on the fence. The book has this wonderful little table that organizes different substituents in two ways. On the left side of the double line are our ortho-pair directors. N with a lone pair, O with a lone pair, OR with a lone pair, N with a lone pair, even if it's got a carbonyl on it. Those are our pi donors. Donate the electrons directly into the pi system. Our sigma donors, alkyl groups or aryl groups, any R groups, those are sigma donors, and we saw they are ortho-pair directing. Halogens, because they are pi donors, are also ortho-pair directing. So anything on the left side of this line, of this double line, are ortho-pair directors. But we have activating groups and deactivating groups. The meta directors were things that could have positive charge or partial positive charge on the ring attached atom. These carbonyls all have positive character on the carbon there. The sulfur does, the carbon is partial. The nitrogen and the nitrogen here have full character. So those are meta directors, but they're also then deactivating. So the halogens are on the ortho-pair directing side, but they are in the deactivating arrow. So we've got ortho-pair directors, meta directors, activating and deactivating. Now let's do a couple practice problems here. We're going to start with a starting material. We're going to use a mixture of reagents to put a group on the ring. And we're going to try to figure out where on the ring our new group is going to go. So let's think about what these things do. First of all, HNO3 and H2SO4, those put a nitro group on the ring. So the question then is, where is it going to go? Now, here's a common point of confusion. Since NO2 is a meta director, some students will confuse putting an NO2 group on with being a meta director. That's not how it works. It's the groups that are already on the ring that are the directors. Don't worry about what we are adding as far as directing or activating or deactivating goes. The methyl groups on the ring will determine where our nitro group goes. So let's think about this. Our top methyl. Methyl is an alkyl group. It's an ortho-pair director. So it is going to direct our new group to carbon A or carbon B. Those are the ortho positions. Or carbon D, its para position. Now remember that for methyl, ortho is favored over para. So A and B is better than D. How about methyl group on the bottom here? This guy also is an ortho-pair director. He's going to direct it to B, which is its ortho, or D, which is its ortho, or A, which is its para. So B is the most blocked, so it's the least likely to proceed. Simply based on sterics, it's between the two groups. So A and D are what's left over. And notice that A and D give us the same product. It's either going to be next to one methyl and two away from the other, or next to one methyl and two away from the other. It's the same product no matter what. So our product will probably be addition to site A or D, since B is more sterically hindered. It's ortho to one, para to the other. Okay, Let's look at this guy. Again, adding an NO2 group to a ring that's got a methyl and a nitro. So our methyl is an ortho pair director. He will direct to A or B. Those are its ortho positions. Notice that we don't have any room on our para position. There's not a hydrogen para to methyl that can be substituted. So top methyl will direct to A and B. Our nitro group is a meta director. It is going to direct meta to itself, which is A or B. So A and B are the same product. If you put something on A, it's the same as if you put something on B. And both of our groups are directing to A or B. Methyl's directing ortho to A or B. Nitro is directing meta to A or B. So our product will have the nitro on group A or B. Let's look at one more. Here we've got two groups on our ring again, and we're going to add a nitro to it, HNO3 and H2SO4. Let's consider what these guys on our ring are going to do to the ring. Now, methyl, again, is an ortho pair director. So ortho is A, para is C. And again, because methyl is small, methyl is going to favor its ortho over its para. So A is better than C as far as our methyl group goes. The methoxy group is going to direct ortho para. Remember that oxygen has a lone pair on it. It's got two lone pairs. So it's going to be ortho para directing. Its ortho is D and its para is B. Now, since OCH3 is bigger than methyl, its ortho group is not going to be its favored. So it's going to favor B over D. So we've got methyl favoring A over C, and we've got methoxy favoring B over D. So methoxy is the stronger ortho pair director. Methoxy is a pi donor. Methyl is only a sigma donor. And remember, we saw that the pi donating effects are much more significant than the methyl sigma donating effects. So our group, our best position is going to be the para from our methoxy. Our methoxy is basically going to win. Think of a tug of war. Which one is trying harder to direct the group? The methoxy is going to win, and methoxy wants to go para. So our position will be on the B position. Now let's consider a couple pathways for doing a synthesis. It says devise a synthesis of para-nitro tert-butylbenzene. The P there stands for para. O would be ortho, M would be meta. So this is para-nitro tert-butylbenzene, which means that we're looking at a tert-butylbenzene with a nitro on the para position, or a benzene with a nitro and a tert-butyl group paired to each other. We want to make this product right here, starting from benzene. So there's two ways to do it. We could first put the T-butyl group on and then put the nitro group on, or we could put the nitro group on first and then put the tert-butyl group on. But think about why this matters. Think about why order matters. The tert-butyl group is an ortho pair director. The nitro group is a meta director. If we put the T-butyl group on first, it will direct the next step para to itself. Now this says plus ortho, but remember that because the T-butyl group is so big, it's really going to be blocking those ortho positions. So by far, the para is going to be more favored. So why is this method bad? If we put the nitro group on first, remember that nitro is a meta director. So if we try to put the T-butyl group on in our next step, those groups are going to be meta to each other because we've got a meta director on when we put our next group on the ring. So that's a problem. If the reaction proceeds, we'll have our groups meta to each other instead of para. Another problem is that it can be very difficult to add groups onto a strongly deactivated ring. Remember that nitro is our strongest meta director, and therefore it's our strongest deactivator. That means our ring really not nucleophilic. It's really hard to add a group to the ring when all of the ring's electron density is being sucked away from it by the nitro group. So if we get a reaction, it would be meta, but it even might not happen at all because the ring is so deactivated. Some books will tell you that you cannot do a Friedel-Crafts alkylation on a deactivated ring. You really can, but yields are poor. So generally it's something that you want to avoid if at all possible. Now, let's look at 4 more, which are really 3 more reactions. In addition to the Friedel-Crafts alkylation, which remember uses an alkyl group and a Lewis acid to add an alkyl group to the ring, the acylation adds an acyl group, basically a carbonyl group, to the ring. It works in very much the same way. We're going to start with an acyl halide, so a carbon with a carbonyl, and that carbon is attached to a halogen. The same way that in our Friedel-Crafts alkylation, our carbon was attached to a halogen. We're also going to use the Lewis acid. That Lewis acid is going to complex with the chlorine, generate positive character on the carbonyl carbon, and it's going to allow the carbonyl carbon to act as our electrophile and add into the ring. An example, here's acetyl chloride. The chlorine is on the carbonyl. We add AlCl3. The carbon bearing the chlorine, also bearing the carbonyl, is the one that gets attached to the ring. These happen in good yields. It's a great reaction, 95% yield. A good thing about the Friedel-Crafts acylation is that really there's 2 things. The first is that you do not get rearrangements. The carbonyl carbon with the positive charge will not rearrange. So we can add linear groups to our ring using Friedel-Crafts acylation, but we can't add linear groups using alkylation because the alkylations will rearrange. We'll get branched alkyl chains. The second good thing about the Friedel-Crafts acylation is that notice that the acyl group on the ring is a deactivating group. It's a withdrawing group, which makes it a deactivator. So that means that the product is less reactive than the ring. Remember that the problem with the alkylation was that the alkylated product is activated. And so we will tend to get multiple alkylations on our activated ring, and there will end up being some unreacted benzene. In this case, the benzene is always going to be more reactive than the product it makes. So once we put this acyl group on the ring, that ring stops reacting, and it leaves the benzene rings free to react with our acyl halide and Lewis acid. If you want to add a single carbon carbonyl to a ring, for example, if we want to make benzaldehyde from benzene, you might think that you would use formyl chloride, just a single carbon carbonyl with the chlorine, along with AlCl3. That unfortunately doesn't work. Formyl chloride is very unstable. So if you just use formyl chloride and AlCl3, the formyl chloride will decompose into carbon monoxide and HCl, and you won't get a reaction. If you also, however, include CuCl, that will cause the formyl cation to form. You don't need to worry about why. It's some weird things going on with d orbital electrons on copper. But remember that for a single carbon carbonyl, you need to modify the Friedel-Crafts acylation by adding CuCl. This is called a formyl group. It's where the name formaldehyde comes from. Basically, we want to add a formyl group onto our ring. We cannot do it using formyl chloride by itself. CuCl allows the formyl cation to form, prevents dissociation, decomposition of formyl chloride, and we get benzaldehyde. This is called the Gatterman-Koch formulation. So it's just like the Frito-Craft's acylation with a very slight modification. Another reaction that's very useful is the Clemenson reduction. The Clemenson reduction will remove a carbonyl. It will reduce a carbonyl if that carbonyl is attached to the aromatic ring. So for example, we could start with benzene, do a Frito-Craft's acylation, add this acyl group onto our ring. Then do the Clemenson reduction. The Clemenson reduction uses a zinc-mercury amalgam along with aqueous hydrogen chloride that will reduce the double bond O to 2 hydrogens. Notice that this is kind of cool because this changes an acyl group into an alkyl group. And the problem with adding the alkyl group was twofold. When we added the alkyl group directly, we ended up getting an activated product, and we ended up getting rearrangements of that product. If we add the acyl group, we don't get an activated product, and we don't get rearrangements. So the trick, if you want to add an alkyl group, even if it's a branched alkyl group, if you want to add an alkyl group, instead of doing the Frito-Craft's alkylation, it's better to do the Frito-Craft's acylation followed by the Clemenson reduction. That will avoid multiple alkylations, it'll avoid rearrangements, and at the end of the day, we end up with our alkyl group anyway. So here's propanol chloride, a 3-carbon acyl group. We can add it to the ring to make this ketone. If we want the 3 carbons in a row without the carbonyl, we just do the Clemenson reduction. That gets us the N-propylbenzene. It would be impossible to add the propyl group directly with Frito-Craft's alkylation because the propyl group would rearrange into an isopropyl group. Notice that this also allows us to convert a meta-director, as is the case for the carbonyl group, into a ortho-para-director, as is the case for the alkyl group. I've got one more series of reactions that I want to show you. This is called the Sandmeyer reactions. Basically, this gives us a pathway to put many other kind of groups on the ring. In this slide, the AR group is short for aryl, or a benzene ring, an aromatic ring. It doesn't mean argon, don't confuse that. So if we've got an aromatic ring with a nitro group, we've already seen that we can do a reduction to convert the NO2 into an NH2. The methods I showed you that before was iron and HCl. You can also do it with H2 and a catalyst, but that will convert the NO2 into NH2. Now again, that NO2 is a meta-director, a deactivating group. The NH2 is a donor. It's a pi donor, so it's a ortho-para-director and an activating group. We can then use this O-No reagent, this hot or cold O-No. This is 5 degrees Celsius. That will convert the NH into N2+. That's an N, triple bond N with a positive charge on the middle N. And that is called a diazo group. Now, the diazo group is very useful because it can be replaced by any number of types of atoms. We can replace an N2, that diazo group, with an OH using these reagents. We can convert it to a chlorine using this reagent. We can convert it to a bromine using this reagent, or a cyano group using this reagent. We can convert it to an iodine using Ki, or a fluorine using this reagent, or back to a hydrogen using H3PO2. So all kinds of other groups we can add. Now, we already knew how to add a chlorine and a bromine and an iodine, but we haven't seen how to convert something into an H or an F or a CN or an OH. Now, why would we ever want to use this pathway to get to a chlorine or a bromine or an iodine when we had other pathways? Well, it's possible that we want to use these other groups for directing effects. Remember that chlorine and bromine on a ring are orthopair directors. So maybe we put a nitro group on so that we can get meta direction. Then we convert it later and eventually put the chlorine on there. So this method kind of allows us to go through different steps that have different directing capabilities. We can go from a meta director to an orthopair director to any of these, which may or may not be ortho or pair directors. These are the Sandmeyer reactions. It's a useful method of converting one or more functional groups into something else. Now, lastly, I want to talk about using these sulfones as blocking groups. I actually see a typo here. This should be SO3H. It's the SO3H groups that are blocking groups. So here I want to make this ortho-vinyl nitrobenzene. Actually, vinyl on a benzene is called styrene. So we could call this ortho-nitrostyrene. But we want to put these two groups on the ring, and we want to do them ortho to each other. Now watch my strategy here. First of all, we haven't learned how to put a vinyl group on. We know how to put a nitro group on, that's fine. But look how we can put a vinyl group on. We can start with a Friedel-Crafts alkylation, or perhaps do an acylation followed by a Clemmensen reduction. But either way, we can get an ethyl group on by one of those methods. That gives us access to our first carbon here, because that is the benzylic position. So we can add Br2 in light to put a bromine on there, and then eliminate it to get to our vinyl group. So our first step is a Friedel-Crafts alkylation, an EAS reaction, but these other two steps are from older chapters. But that's how we get a vinyl group on. Now, remember that vinyl, being an R group, being a alkyl chain, is an orthopair director. But because it's bigger than methyl, it's going to favor para over the ortho positions. So if we try to add our nitro group on now, that nitro will go para. We have a problem. Also, we don't want to put our nitro group on, because if we put our nitro group on, everything else that happens after that will go meta to the nitro group, since the nitro group is such a good meta director. So the best we can do is put on our vinyl group, but then we want to put the nitro group on after that. So what we do is we use a blocking group. Remember I said that we can easily remove SO3H from our ring after we put it on. So we put it on, SO3 and H2SO4, and again, that's going to go para because the vinyl group is a para director. Now look at what we have here. In a subsequent reaction, the vinyl can only direct a group to its ortho positions. And SO3 is a meta director. SO3H is a meta director. So the two positions that we want, ortho to our vinyl, are the only positions that the vinyl group can go to, can direct it to. And it's also the only positions that the sulfone group is going to add to, is going to direct to. So the positions that we want are being directed by the vinyl now, ortho to the vinyl, and meta from the sulfone group. So now we can add our nitro group. It's going to go ortho to the vinyl, meta to the sulfone. In our last step, we can just remove the sulfone group with H2O, H2SO4, and heat. And voila, we've got our product. So that's how we can use blocking groups. Pretty much it's useful for putting something ortho when it would otherwise go para. You put the blocking group on the para, the next step will put everything ortho. So that's the end of lecture 8. For workshop, you can do two things. The EAS section, electrophilic aromatic substitution, basically the last part of this lecture is chapter 19 Instrumentus, and Diels-Alder is covered in chapter 17 and 18 Instrumentus.